Imagine our planet, Earth. From space it looks like a beautiful blue marble, calm and still, but this quiet image hides a powerful secret. The ground beneath our feet is not one solid piece. It is actually a giant puzzle made of enormous slabs of rock. We call these puzzle pieces tectonic plates. They are constantly moving, floating on a layer of hot, soft rock deep inside the Earth. This movement is called plate tectonics. It is a slow but unstoppable force that shapes our world, building mountains, causing earthquakes, and creating the vast, mysterious landscapes hidden beneath the oceans. This is the story of how our planet is alive, constantly changing and rearranging itself over millions of years. This idea is a huge one. It tells us that the continents we know today were not always in their current places. They have drifted across the globe, like giant ships on a cosmic sea. The Atlantic Ocean, for example, is getting wider every year while the Pacific Ocean is slowly shrinking. This happens because the tectonic plates are moving. Some are pulling apart from each other, some are crashing together, others are grinding past one another. This dance of the plates is responsible for almost all of the major geological features we see on Earth's surface, from the highest peaks to the deepest ocean trenches. It is a fundamental process that makes our planet dynamic and ever-evolving. To understand this, we have to journey deep inside our planet. Below the crust, the part we live on, is the mantle. The mantle is mostly solid, but it behaves like a very, very thick liquid over long periods. Think of it like honey or thick tar. Heat from the Earth's core creates slow-moving currents in this mantle material. These currents act like a giant conveyor belt, dragging the stiff tectonic plates that float on top of them. This movement is incredibly slow, usually only a few centimeters per year. That is about the same speed that your fingernails grow. There are three main ways that tectonic plates interact at their boundaries, at their edges. The first type is called a divergent boundary. Here, two plates are pulling away from each other. As they separate, magma rises from the mantle to fill the gap. This magma cools and solidifies, creating new crust. On the ocean floor, divergence forms enormous underwater mountain ranges. The second type is a convergent boundary. Two plates move toward each other, resulting in a collision. What happens next depends on the types of plates involved. If a dense oceanic plate collides with a lighter continental plate, the oceanic plate bends and slides beneath. Subduction. Subduction recycles old oceanic crust back into the mantle. If two continental plates collide, they crumple and fold, pushing upward to form massive mountain ranges like the Himalayas. These are some of the most dramatic and powerful places on Earth. The third type of boundary is a transform boundary. Here, plates slide horizontally past one another, the rough edges get stuck, pressure builds, and when they slip, powerful earthquakes occur. Divergent boundaries are the birthplaces of new ocean floor. Convergent boundaries recycle old crust and build giant mountains. Transform boundaries are the stress points where friction is released in violent shaking. Together, these interactions account for the vast majority of our planet's earthquakes, volcanic eruptions, and mountain-building events. Evidence for this dance surrounds us. Coastlines like South America and Africa seem to fit together like puzzle pieces. Identical fossils appear on now separated continents, and today we can measure plate motion with GPS. With science we can rewind the clock. See Pangea forming about 300 million years ago, then watch it break apart as the Atlantic opens and India heads north toward Asia. The slow dance continues. Plates still move today, reshaping our world in ways we can measure and imagine. Now let's dive beneath the ocean's surface to see these forces at work. The first feature we encounter is the mid-ocean ridge. This is not just a single mountain, it is the longest mountain range on Earth, stretching over 65,000 kilometers, like the seam on a baseball. It is the result of a divergent plate boundary. First, two oceanic plates begin to move away from each other. Pressure on the mantle drops and hot mantle rock melts into magma. Magma rises, meets cold seawater, cools quickly into new oceanic crust. That new crust attaches to the plate edges, forming a raised volcanic ridge. The ridge is youngest at the very center and older as you move away. It is a volcanic world dotted with hydrothermal vents supporting unique deep-sea ecosystems. A perfect real-world example is the Mid-Atlantic Ridge, running from the Arctic to the Antarctic. Iceland is special. Here the ridge rises above sea level and scientists can walk it. If ridges are where new crust is born, trenches are where it goes to die. These are the deepest parts of our planet, the long, narrow canyons of the seafloor. Trenches form at convergent boundaries where an oceanic plate collides with another plate and is forced to sink. The bending and descent create a V-shaped depression we call an ocean trench. As the slab sinks, heat and pressure can melt rock, producing magma and volcanoes on the overriding plate. Stress can build and release as megathrust earthquakes, displacing the seafloor and generating tsunamis. The most famous example is the Mariana Trench, nearly 11,000 meters deep at Challenger Deep. If you placed Mount Everest in the trench, its peak would still be covered by over 2 kilometers of water. Beyond ridges and trenches, the ocean floor is dotted with thousands of individual mountains. Some rise so high they break the surface to become islands, others remain submerged as seamounts. Some volcanoes form in the middle of a plate over hotspots, stationary plumes of hot mantle rock. As the plate moves, a chain of volcanoes forms. Only the volcano over the hotspot is active. Over millions of years, islands erode, sink, and can become flat-topped seamounts called guyots. The Hawaiian Emperor chain records the Pacific Plate's direction and speed over tens of millions of years. From the creation of new crust at ridges, to destruction in trenches, and volcanic punctuation of hotspots, these forces create dramatic highs and lows. And everywhere else, the slow rain of sediment smooths the ocean floor into vast plains. Together they sculpt the seafloor, creation, destruction, and gradual burial by sediment, a dynamic canvas. Now let's visit the most common landscape on our planet, the abyssal plain. Finally, after exploring dramatic mountains and deep trenches, we arrive at the abyssal plain. These vast, flat expanses cover more than 50% of the Earth's surface, and are among the least explored places on Earth. The abyssal plain is the final resting place for material slowly drifting down from sunlit waters above, microscopic shells, dust, and river silt. Sediment accumulates only a few centimeters per thousand years, but over geologic time can form kilometers-thick layers. This thick blanket buries the rough basaltic seafloor, smoothing hills and fissures into one of the flattest natural surfaces on Earth. Appearances are deceptive. Beneath the sediments, the rugged foundation remains. You can find abyssal plains in every major ocean basin. The Somme Plain in the North Atlantic is one example. But large parts of these plains remain unexplored by humankind. In conclusion, plate tectonics creates the dynamic highs and lows of the seafloor, ridges where crust is born, trenches where it is recycled, hotspots that form islands, and sediment that paints vast plains. The ocean floor is a dynamic canvas, constantly being painted and repainted by the grand, slow art of plate tectonics. Students will be able to explain plate tectonics, identify ocean floor features, and describe how plate motion creates those features. Thanks for joining this journey beneath the waves. Explore more to see how these processes continue to shape our world.